Hi everyone. So we left off with lecture 2A on this slide called Refining the View, discussing the interior of Earth and how we understand the different layers that exist within Earth's interior. I mentioned that it was through seismic waves or earthquake waves that are able to travel through certain layers and not others. Specifically, it is the outer core of Earth that is made of liquid iron and nickel that actually these seismic waves cannot pass through. So they bounce off the outside of it and are recorded in seismic stations around the world, and determining the time it takes for the wave to travel from one location on the sphere and bounce off that layer and to another location is the subject of what seismologists study. And these are people that study earthquake waves, and they're the ones who've helped us determine the interior structure of Earth and eventually its composition. I wanted to reiterate those things and start out on this slide today because we are discussing also something called Earth's magnetosphere, which I'll mention in a moment. And the magnetosphere is the extent to which Earth's magnetic field exists from the inside of the Earth all the way beyond it. And the magnetosphere is created also as a result of this liquid iron in the outer core. And the liquid iron in the outer core, as it moves around, as Earth orbits the sun and spins on its axis in a 24-hour day, and continents, plate tectonic processes are occurring, and elements and rocks are being transferred to and from the different portions of the interior of the Earth. This liquid iron outer core is moving around, and while it's sloshing in the interior of the Earth, it creates something called a geodynamo, meaning that it creates a machine basically that perpetually creates a magnetic field. And this is the magnetic field that we'll talk about today. So, just as mentioned, Earth is surrounded by a magnetic field that is caused by the geodynamo. And this is what causes your compass to point north or south. And the geodynamo is very complicated in terms of mathematics and physics, but we can think of it as acting like a bar magnet with a north pole and a south pole. And that north and south pole are what create magnetic field lines that go into and out of them and dictate in which direction our compass points on different places on Earth. So importantly, the North Magnetic Pole and South Magnetic Pole are not on the geographic poles. They're offset to some degree, and that's important for understanding magnetic properties of Earth. But the magnetosphere is the region protected by Earth's magnetic field. So on the bottom right, we have a picture of the magnetosphere. And the magnetosphere is important to Earth because it deflects something called the solar wind. So these are rays of energy from the sun, and they are highly ultraviolet, and those rays would contribute to extinction of life on Earth were it not for the magnetic field, because they are so strong. So in addition to the rays that are deflected, there are also the Van Allen radiation belts that trap that energy that doesn't get deflected. And although some of it does, and so if you've ever heard of the northern or southern lights, that's some of the ultraviolet radiation that does reach into Earth's magnetosphere and those are the particles coming down from the poles that generate the aurora. So that's the magnetosphere. The Earth's atmosphere is another one of Earth's spheres, and this is, of course, the layer of gas that surrounds Earth. It's mainly composed of nitrogen and oxygen, 80% and 20% respectively, and it creates air pressure on its surroundings. So the lower atmosphere is where most of our clouds are and wind, and that's a result of all of the that's a result of the high density of gas particles that exist in the southern atmosphere. So if you look on the left side diagram, you'll notice that on the bottom there's very high density of particles. They're very close together. As you move higher into the atmosphere, then the particles become less dense. And that's the reason why it's so very difficult to breathe at higher elevations on the tops of mountains. And of course, if you were to go into the upper atmosphere, there's hardly any oxygen at all. So humans and life is very difficult for them to survive. And on your diagram, you have just some images for scale. Mount Everest, Earth's tallest mountain, at about 9,000 meters, the height of a commercial jet and a military plane, balloon flights, all part of the atmosphere. The water spheres are the hydrosphere and cryosphere. The only important thing to remember from this is that the hydrosphere covers about 70% of Earth's surface, and about 97% of that is salt water, with only 3% being fresh water. And the geosphere, we can think of its surface as being expressed through bathymetry, which is the depth of the ocean, and topography, which are the depths or elevation of the land. So these are basically elevation on land versus elevation on continents. The materials of the geosphere are comprised mainly of only a few elements. Even though there's about 92 naturally occurring elements on Earth, only 4 of them, iron, oxygen, silicon, and magnesium, make up 90% of Earth's mass. Okay, so most of the materials on Earth, in terms of mass, you can think of it as weight, is made up of iron, oxygen, silicon, and magnesium. So you may imagine that most minerals and most rocks have these elements as their components. The basic categories of materials, which we'll discuss in Chapter 3 in more detail, can be lumped into melts, magmas, lavas, glasses, minerals, sediments, metals, and rocks. And I'm not too keen on these, the way that this slide is ordered, although the definitions are correct. I will provide a better visual, I think, in the future about different materials. And then there's the biosphere, of course, where life exists and organic chemicals are produced by living organisms. This biosphere actually extends above the surface and below the surface for several kilometers. Anywhere where there is organisms, microorganisms, that includes the biosphere is included in that area. So we don't talk much about the biosphere in this class, although increasingly geosciences is becoming more related to biogeosciences as we understand Earth systems better and in more detail. Finally, I want to introduce you to a little experiment completed by a natural scientist in 240 before Common Era. His name was Eratosthenes, and he was able to provide a very good estimate for the circumference of Earth and determine that Earth was a sphere as a result of an experiment he did. So I'll just mention his experiment rather quickly. Basically, he and his colleagues measured the shadow cast by the sun's rays at 12 o'clock noon on the same day in two different locations at two different latitudes. So the latitude at point A and latitude at point S. And the latitude at point A cast the shadow on this particular day, and the latitude at point S directly beneath it did not cast a shadow. And from that, Eratosthenes determined that the angle, the important angle derived mathematically or geometrically from this shadow was 7 degrees, and its conjugate angle also would be 7 degrees. And that was, he used that angle and the distance from point A to point S to calculate the radius of Earth. So something that you may have learned in geometry class, you could apply to create this experiment. So that's how we know Earth is a sphere, through Eratosthenes' original experiment. Of course, we've had it validated over and over again over the millennia. Another question I'd like to ask is, how do we know the bulk density of Earth? If the average density of matter in Earth is 5.5 grams per centimeter cubed, the average density of crust is 2.8 grams per centimeter cubed, and the average density of the mantle is 4.5 grams per centimeter cubed, would the density of the core be less than average Earth, less than crust, less than the mantle, or more than the mantle? This little thought experiment is reminiscent of something called the Cavendish experiment, which was done by Henry Cavendish in around 1800, where he was determining the average density of Earth. Very important experiment for future studies. And finally, for the end of lecture 2, lecture 1B, I would like to ask you these questions. What types of geosphere materials do you interact with on a daily basis, and how? And even though we know that 70% of Earth's surface is covered in water, why then do we so frequently hear of drought being an issue? Thank you.